Hi everyone, I wanted to do a video on the where magnetism comes from, because in the book it doesn't really go into this, and I'd like you to have a notion of what the origin of magnetism is. From what you've read already and you've seen in the past, you should know that when you have, for example, this is a wire and these are electrons and they're traveling through the wire, this produces a magnetic field. Using your right hand rule you can see what the direction of the field lines are, and so that shouldn't surprise you very much, and hopefully. And but let's think about materials and why you can produce magnets and make materials which retain the magnetism, and then and use those, or why we can induce certain magnetic properties in materials if we put them in an external magnetic field and things like that. Let's think a little bit about atoms for a second. Let's draw an atom. Well, first the nucleus. If that's the number of protons, for example, and here we have neutrons, and that's the nucleus of an atom, and then whizzing through the around it you've got these electrons going in all sorts of directions and orbits. And the same way as here, when you have a flowing charge you produce a magnetic field, these electrons that are going around the atom will also have produce magnetic effects. They're traveling in just in space and not inside of a wire, but they're still moving charge and they're producing magnetic effects. So some atoms have well, the magnetic effects that they have, normally we give it the name of the magnetic moment of an atom. And depending on the type of atom and what the electrons are doing and everything, the material will have different properties. So you have three types of magnetic materials, and they depend on the type of atoms they have, obviously, because that's the definition of a material. And the first one is diamagnetic materials. Diamagnetic materials, and they are not susceptible to magnetism, so they resist magnetism. That's what it means. And so what happens if this is the nucleus of the atom, for example, some of the electrons are, well, mostly they're paired up, but some of them are rotating in that direction, and there will be, for as many as rotating in that direction, they will be paired up with ones that are rotating in the other direction, and most materials have this. So what happens is that you don't have an overall magnetic effect, because they kind of cancel each other out. And so when you have an external magnetic field and you put these atoms in there, then they don't they kind of cancel the effect, and they don't have an overall alignment in the direction of the magnetic moments, and so they don't exhibit magnetic properties. Especially later, when you switch off the external magnetic field, they definitely don't retain any kind of magnetic properties about them. So those are diamagnetic materials. And number two would be the paramagnetic materials, and these would have more unbalanced numbers of electrons. So they will have maybe a couple, not that many, but maybe one extra electron going in one direction, which is not paired, and therefore they're slightly susceptible to magnetic fields, and they can exhibit magnetic properties. But when you switch off the external magnetic field that you're trying to use to make the material into a magnet, then the effect wears away. So let me just write some examples of these, or of each one, so you have a bit of a notion of what type of materials they could be. So diamagnetic materials, for example, are most of the ones in the periodic table, but examples could be copper and silver and gold. So these would be material elements that you wouldn't want to make a magnet with. They wouldn't work. Paramagnetic materials would be ones such as magnesium, lithium, tantalum. Might not have heard of that one already, but anyway, I've just looked these up because I don't know them off by heart, but it's good to have a notion of what these could be. So once again, the rotation of the electrons and the direction in which they rotate kind of cancel each other out because they appear in pairs and they're all nicely balanced atoms, so then you can't really induce very much magnetic behavior. Here you've got some left over, maybe 1 or 2 electrons left over where you can produce some magnetic effect, but when you switch off the external field that you're using to induce some kind of permanent change in the material, then they go back to normal and they don't really keep that behavior. And third are the ferromagnetic materials. So ferro comes from iron, because iron is a good one. Ferromagnetic materials. And these have not only the property that they have plenty of electrons unbalanced, and therefore they can produce overall magnetic moments, but also the material has sort of whole sections which we normally call magnetic domains. And they are maybe 10 to the 12 atoms in a row, which are sort of aligned with one another. So when you come with an external magnetic field and you try to induce some magnetic behavior in these, and they all align in the same direction, you get loads of magnetic moments in the same direction. So they all go in a row, and then when you switch off your external magnetic field and you go away, that the material is left there all still aligned. So then you've got a permanent magnet there, and you can then check that it's got the poles are created, and then you would have a north pole on one side and a south pole on the other, and you could see the field lines going from one to the other, and then you would have a permanent magnet. So materials that do this are for example iron. It's a very good one. That's where the ferro comes from there. Cobalt and nickel. These are 3 examples. And they what happens when there is no external magnetic field on them is that all these domains are in random direction, so overall there's no magnetic effect. But when you put an external magnetic field on them, then they all align, and then you get a large magnetic effect. And that's a pretty bad drawing of what I mean. So just to show you a little bit better what I'm talking about, here you have on the left, this would be an unmagnetized material, where these guys there, they are the domains. So they are large regions where millions of atoms and trillions of atoms are pointing in a similar direction, but since these domains are kind of randomly spread out, then the overall effect is that it's not magnetized. But after we apply an external magnetic field, and this is a ferromagnetic material, then this happens. All the domains align, and then you get a permanent magnet even when you switch off the external magnetic field. So this is a magnetized material. Okay. And so another diagram that I wanted to show you also was this one over here. You can see the magnetic field lines there, and the magnetic field lines, like pretty much any other field lines, electric and gravitational lines, they don't exist. They're just representations, but they're a pretty good way of visualizing what's really going on. And Here we don't have direction, so we haven't included which way the lines are actually going, but outside of the magnet, this is the North Pole and this is the South Pole. The lines always go from the North to the South Pole, so they would go like that in that direction and in here, and they would go from here and then in that direction and into here. So all the lines would go kind of like that, and they would also go in that direction like that over there. And if you pay attention, you can see a few different aspects of this which are useful to know. For example, one of the important things that you should know is that the field lines, magnetic lines, same with electric in this case also, magnetic field strength lines, they never cross. Okay, they don't cross, they're always kind of like that, they go alongside each other. Another thing is the density signifies the strength of the field, so as you move further away from the poles, the lines are less dense, less close together, or less dense. So this means weaker magnetic field strength. So that should make sense. And then another one is that the direction goes from north to south of the field lines, always outside of the magnet. But inside of the magnet they go from south to north, right? Because this is the south, and inside here there's also lines going like that. So they go from south to north and then out. So they form a closed loop like that. These go like that, inside, and then like that. And these go like that, and then like that. So hopefully that makes sense. And one last thing that I wanted to mention, I talked before about the right-hand rule for the magnetic field around the flowing current, and I wanted to show you a bit of a better picture. And here it is. So the current is going upwards in the diagram, and you put your right hand along it and you around it, and you put your thumb in the direction of the current, and you get the direction, your fingers point in the direction of the magnetic field lines. So one thing I wanted to mention that's important is that if this is the current, if this is the wire, and that's the direction of the current as we normally call it, the current is I, that means the electrons are going in the opposite direction. I hope that you know what that means, and it's a bit of a weird convention, and it's because of a guy called Benjamin Franklin, basically. And what he said was that he said that what was responsible for the current, electric current, was positive charges moving. So he gave that direction to positive charge, and then when later on it was discovered that it was really a negative charge, and the electrons that were carrying the current, so they would be going in this direction, while the current was going in this one by convention. The electrons would be traveling in the opposite direction. And when they discovered that, they'd already written like so many equations and books and using that convention for the current that it just stayed. So therefore this thumb points in the direction of conventional current, and that's the field around the fingers. Okay, but the actual electrons, it's important to know that the actual electrons are actually traveling in the other direction. Yeah, I just wanted to show you quickly a picture of the guy, and this was, if you read in Wikipedia a little bit about him, he was a really interesting man. He was a polymath. He was a mathematician and a physicist, and he was a politician, and he wrote one of the first newspapers around the time in the US, and he was one of the founding fathers of the USA, wrote the Constitution and helped to write the Constitution, and all kinds of stuff. So check him out if you have a moment. Benjamin Franklin. Alright, this should be enough for the first class on magnetism.